Welcome everyone to another BGCSE past paper review. Today we are reviewing a physics paper, which is a paper 2 from the year 2021. Please remember before you start the examination, always write a school number, your candidate number, your surname, and your initials. Again, read through the instructions before you start the examination. And if you have any queries, please clarify those with the examiner. Now let's go to the first question. It said, a warehouse owner has to stock 40 identical metal blocks, each of weight 1,500 newtons, on the floor in a storage room. So for figure 1.1, it shows a top view of the dimensions of the block. And so if you look at the block carefully, what you notice here, we have a dimension of 0.6. Also, the thickness of it is 0.1 and the height of it is 0.45 meters. Now, the next part of the question here, well, not the next part, the next statement based on this question is that figure 1.2 shows two possible options of stocking the metal blocks the warehouse owner is considering. It's in order to minimize pressure exerted on the floor, he seeks to determine the pressure exerted by the metal blocks when standing laying flat, which is case 1, and standing on one end, which is case B. All right, and so that's figure 1.2 that is actually showing it two different options that you may consider to do this. So for part A, it's what is the volume of the metal blocks. So the volume of the metal blocks will be here, which is the 3-dimension. Let's go back here to see if we get all of them. So let's go up here quickly. All right, so the metal block, notice the dimension here, which is 0.6, 0.45, and then we also have here 0.1. All right, so that's the dimension there of the block. All right, and so let's quickly just calculate that. So what is the volume of the metal block? And so the metal block going to be 0.6, 0.6, all right, and that we multiplied by 0.1, which is another dimension there. Let's put my multiplication sign, 0.1, and then multiply that by 0.45. And what we get there as a result for the block is 0.027, and that will be meters cube. All right, so that is the volume of the metal block. All right, so calculate the area in contact with the shelf when the 40 metal blocks are stacked one on the other while laying flat. All right, and so to get this, what we're going to do here, find the area. So let's go back to the area right here. And the area, if you notice, this is in case 1 here. So in case 1, to lay flat, the area will be the base times width based on what we're seeing here. So this is 0.6 multiplied by 0.45. All right, so let's do that real quickly. So it will be 0.45 multiplied by 0.6. All right, and so the area will be, the area of contact will be that, which will be 0.27 meters square. All right, so that's the area of contact in case 1, in case A. One next part of the question is to calculate the pressure exerted by exerted on the shelves by the 40 metal blocks in case A. So what we're going to do here, now we already have the force, and so let's go for the weight of a block. I'm going to show you the weight of a block, and we need to know that, and we want to find pressure. So pressure is force over area. So the pressure here will be the force, and remember that one block, let's go back to the first part of the question here, that a single block is 1,500 newtons, okay? There's 1,500 newtons for one block, and so let's calculate that real quick. And so here now, you're going to be the force, because remember that pressure is equal to force over here. Let me just write that for you. Pressure equals to force divided by the area. And so if force divide is pressure is equal to force over area, then the total force will equal to, let me just put that here, F would equal to the 1,500 multiplied by 40. All right, and so here we're gonna get 60,000 um, 60,000 Newton. Okay, so 60,000 Newton as the total force for all the blocks. And then remember the area that we just calculated if it lay flat in case A. So the area is 0.27. And so if the area is 0.27, then what we're going to do here is going to say 60,000 divided by 0.27. All right. And that will give us a total of 222,222.22. So there's all twos. It's going to be 2, that 222,000, 222.22. All right, so it's all twos. And then this is going to be Newton per meters squared. All right, so that will be our pressure on the floor by the 40 blocks. All right, so let me just put a little comma right here so you get to see the exact value. So it's 222,222.22. All right, so let's go to part C. For part C, said the 40 metal blocks are allowed to stand on ends as shown in case B. And we already see what case B is. I'm going to go back a little bit so you can see dimensions. It said without further calculation. Okay, so without further calculation, predict the magnitude of the pressure exerted on the shelf by the 40 metal blocks in case B in relation to that in case A. All right, so what I'm going to do now is to go back and show you something really quickly. And so in case B, if you notice here that this area is smaller. So the area of contact is smaller compared to in case A. So case A have a greater area of contact. In case B is a smaller area of contact. So without further calculation. So they do not want us to calculate the pressure here. They just want us to base on the knowledge that you know. And so here now, it said, without further calculation, predict the magnitude of the pressure exerted on the shelf by the 40 metal blocks in case B in relation to that in case A. So based on what we know here for case A, we have 222, we have 222,222.22 Newton per meter squared. This is also a Pascal as well. So let's put our Pascal right here. So you can just put your unit as Pascal because 1 Newton per meter squared is also a Pascal, right? Okay, so without any calculation, what we can say here is that the pressure in case B, so we're going to say the pressure in case B, all right, so in case B, all right, will be greater, and let's say greater than, let's put all of this, so greater than 22,222.22, let's call this, let's say Pascal or Newton per meter square, doesn't matter. All right, so it will be greater than that for sure. So the pressure in case B will be greater than that in case A. So you can even say it as that without even using the numbers, but it must be greater than this value, must be. All right. All right, so just to make a note right there. All right, so pressure in case A will be greater than pressure in case B will be greater than pressure in case A. So wherever you put it, you could also do that. What you can also do is to put the greater than sign, and so the pressure will be greater than 222,222.22. Is to give a reason for your response. And the concept right here is that smaller area of contact, all right, smaller area of contact result in all right, let's say smaller area of contact with the same force, because remember now the weight will be the same. All right, so smaller area of contact with the same force, with the same force result in, with the same force result in a greater pressure. All right, so with a greater pressure, if the same force is used for a smaller area. Also, what you can also note is that pressure is inversely related to area. Is it inversely related to area or area of contact, right? All right, one based on the formula, let me show you the formula. So what I'm saying now, based on the formula, as area increases, or let's use decrease because as in case B, the area decrease. As area decreases, then the pressure will increase because remember that pressure is equal to um, force over area. And so if you think about it carefully, you will notice that if you have a bigger area, then the pressure must be smaller. So if the area is smaller for the same force, then the pressure will be a greater value. All right, so we know that for sure. All right, so that's cover that part. Let's go to question number 2. In question number 2, so this question is about about gas laws, and so here now it said figure 2.1 shows the parts of a typical here hot air balloon. It said prior to its ascent, the balloon is filled with air and heated. The envelope is made of elastic material, which stretches when the pressure inside the balloon is greater than the pressure outside. And so let's go down a little bit. So the envelope right here, which is the balloon as you would call it, it is elastic, so it can stretch. All right, and so here you have a deflation port that is right there. All right, and so we have the mouth or the throat, and then we have the burner, then we have a basket that the persons will be in, and then we have also a portion here that is called a skirt. All right, it said now for figure, well, part A said when the air is heated, what happens to the kinetic energy of the gas particles? And so once it provide more heat or a higher temperature, as remember that kinetic energy is proportional to temperature. So once heat is applied, then the kinetic energy will increase. Okay, so it will increase. Okay, so higher temperature, higher kinetic energy. And of course, why? Because the particles move faster as well. All right, because of more kinetic energy. All right, so volume of gas contained in the balloon. And so again, if you apply heat, then what's going to happen to the volume is also going to increase as well. And that's why it is elastic. A matter of fact, it's actually stated in this statement earlier. All right, so this is going to also, the volume will increase. All right, so it will increase as well. All right. Now, so the density of gas within the balloon. So the density, what happened to the density? Now, remember now, if you increase volume, because density is mass over volume, all right, so if you increase volume, then the density will decrease because remember the mass will be the same, so mass will never change. But increasing the temperature increases the volume, and so therefore, if you have a greater volume for the same mass, then the density will decrease. All right, so let's say it will decrease. All right. Okay. All right, let's go to part B now. So for part B here, it said as altitude increases, atmospheric pressure decreases. So as you go higher, the atmospheric pressure will decrease. Now, it said what effect, if any, would the decrease in atmospheric pressure have on the volume of the balloon? All right, so if you have less pressure on the outside, so as pressure decreases, then the volume will increase, all right, because less pressure on the particles, the particles can move more freely apart from each other. So therefore here, it will increase, okay? And remember the law, which is Boyle's law. If you increase pressure, then volume will decrease. All right. So increase pressure, you have a decrease in volume, and that is based upon Boyle's law. All right. All right. And so just remember that pressure and volume are inversely related. Pressure and volume is they're inversely related based upon Boyle's law. All right, let's go to the next question now, or part of the question here. So it said no in figure 2.2 shows a pressure volume graph of a fixed mass of gas. So the mass will be the same. And here we have the pressure on the Y, the volume on the X. And if you notice here, as the increase in volume, then the pressure will decrease. And this is actually showing Boyle's law, as we stated that pressure and volume, they are inversely related. So here now for part one, it said under what condition must the reading have been taken? And so if we look at the graph, we're looking at pressure versus volume. So remember that there are three things that actually affects the gas. And so one is pressure, volume, and temperature. So those are the three things that are related, or the properties that will affect how gas behave. All right. So here now, we're going to say here that the constant temperature must be a constant temperature. Temperature must be kept constant. And again, this is for Boyle's law. If you notice that what we're investigating here, this is Boyle's law. All right, it's a constant temperature. All right, so that's constant temperature. Remember that boys can't take the heat, right? Remember that we went through that. All right, so that is Boyle's law. And so what is the volume of gas when the pressure is 5 atmosphere? So we look at 5 atmosphere and find out what is the volume of gas. So let's go to the graph. And all you need to do is to really just mark the line. So let's just use the highlighter. So we're going to mark the line at 5 atmosphere. You're going to come all the way down here. So yeah, the 5 atmosphere, what will be the pressure? And so that give us 100 ml. So notice that is 100 ml right there. Let's put this in real quick. So this is 100 ml if the atmosphere is 1. All right, so 100 ml. So what is the pressure when the volume is 400 ml? So let's go back to the graph again to figure this out. Looking for 400 ml. So let's go to here. All right, let's change this so we don't confuse ourselves. All right, so yeah, let's go to the red. All right, so 400 ml. You come here, and then you're gonna see, I notice here, oh, we're actually going, it's a little bit above. Let me use a final line here. If you notice, where the line actually meet, this is a little bit above the one value. All right, so somewhere there. All right, so it's not in the halfway, it's way below the half. All right, so what I'm gonna do is can estimate based on where it actually falls, and so it will be about 1.2. Okay, I guess they will give you a little bit plus or minus value, so you can say 1.1, 1.2, 1.3. I mean, I'm sure that they're going to pass 1.3 in terms of errors, right? Because there is no small markings to actually say, okay, it's 1.2. So I'm going to estimate approximately 1.2 here, and this is going to be atmosphere, all right? All right. So it's a describe the relationship between pressure and volume. As we said earlier, pressure and volume, they are inversely related, right? And this is based upon Boyle's law. So they are inversely related. I said they're inversely related. All right, so part E now is on figure 2.2, sketch the curve that would be obtained if the experiment was repeated at higher temperature. So now if you should change the temperature, make the temperature higher, let me just go back to show what is happening here. When you increase temperature, what will actually happen is that the volume will increase, right? And again, if volume increases, what you're also going to get as a result of increased temperature is that the particles going to move faster and they're going to bombard more onto the walls of the container and also increase pressure. So this now is a combined law. And so what will happen here that both pressure and volume will increase if you should increase the temperature. So what you're going to have is a graph looking something like this. Once it's higher than the first one, both of them are higher, then yeah, the graph will look something like this. Higher volume, and what you also get is higher pressure as well. But what remains, what the curve look the same, is that the relationship, let me just write it down, the relationship between PV over T is actually give you a constant, right? So the graph will look alike, but just higher, all right? Because higher temperature, higher pressure, higher volume must give you what they call a constant. All right, just please remember that relationship, that P times V over T is equal to a constant. And such our curve will look almost identical, but just higher. All right, and remember that T is always the denominator in the equation. All right. All right, so let's go down to the next part of the question here, which is the last part of the question. It's a bubble of gas rises from 80 meters deep in a body of water to the surface. What happens to the volume of the bubble as it rises? So what you need to remember in terms of water is that the deeper you go, the pressure is greater. So the higher you go to the surface or closer to the surface, the pressure is less. So if there is less pressure to the top as the bubble rises, then less pressure is on the gas particles. And so therefore, as pressure decrease, then what we have is an increase in um, volume, right? So an increase in volume. All right, so the gas bubble get bigger. So as it go up, if you look at this carefully in the water, if you should blow with a straw slowly into a cup with water, and you blow through the straw at the bottom of the water, you notice as the bubbles come up, they get bigger and bigger, and simply because they're increasing size, because as they come to the surface, the pressure is less. All right, so it's a nice, cool experiment to actually view. Very simple and nice. You can do it at home without any form of danger. All right, so question number 3 is the question is about Newton's law of motion. And here now it says what you have here is a speed time graph and momentum. It said, given the speed time graph below, answer the following questions. All right, and so let's just run through real quick. We have speed, we have time. All right, and so here now for part A is a calculate the acceleration of the object during the first 10 seconds. So acceleration is equal to v minus u, which is the change of velocity. So when I just say v minus u, which is the final velocity minus initial velocity over a change in time. All right, and so let's just say time over time or change in time. And so right here, if you look at the first 10 seconds, let's go back a little bit to the graph. In the first 10 seconds, what we need to look at is that the 10 seconds here, which is going up here, then going across. So the change that takes place right in terms of velocity or speed is that it moves from 0 to 15, and then for 10 seconds it's from 0 to 10, right? And so to calculate this, what we can do, we can just simply say that change in velocity is the final velocity is 15 minus 0, which you don't necessarily have to minus 0 because you can just say 15. All right, and that's going to be divided by 10 minus 0 as well. All right, and so as you know this, you're going to be 15 over 10, right? You can just say or 15 over 10. Really don't matter if you use 0 or not, because 0 from anything is the same value. And so here now the acceleration is 1.5 meters per second squared. All right. All right, so now let's go to part B. It said, what physical quantity is represented by the area on the curve of the graph? And once you have a distance time graph, the area below the graph is always, once you have a speed time graph, the area below the graph is always the distance traveled. Okay, so just to make a note as that. The velocity time graph or speed time graph, the area below the lines or the graph is actually the distance traveled. So let's say distance. All right, if it was a velocity, you could put displacement, right? But since it's speed, let's say distance, because distance is scalar, displacement is vector. All right, so for part C, is if the object has a mass of 100 kilograms, right? Calculate the force on the object in 10 seconds. And so the formula for force here is going to be, let's say the formula for force is equal to mass times acceleration, right? Remember, we can also find force as formula as weight, because weight is equal to mass times gravity. But this object is not falling, right? So you cannot use that formula. I just want to point it out. So weight, if something is acting downwards, then you can just use mass times gravity. This is not acting downward. This is going actually a moving object, which is, you can actually call this on the horizontal plane. And so the mass times the mass times acceleration will give us our force. And so our mass here is 100 kilograms, and our acceleration that we calculated earlier, I must go back to remind you about it, since you might forget, is 1.5. And so going to be multiplied by 1.5, which equals to here 150 newtons. All right. So the force there is 150 newtons. And let's go to the next part of the question here. So part D is to calculate the momentum of the object between the times of 10 and 20 seconds. So let's go to the graph to see exactly um, what is going on there in terms of what we should calculate. All right, so we'll, first thing you need to know what momentum is. Momentum is actually, let's put that as momentum. I'm put P, but it's not an exact P. There's a small thing on the bottom as you should remember. So momentum is equal to mass times velocity. So we need to know what the mass is. We already know what the mass is because we just use the mass, which is 1,000. The mass is 100 kg. Okay, so we know that. Let's find a velocity between 10 and 20 seconds. So let's go back to the graph for that. All right, so the velocity here between the 10 and the 20 is a constant velocity, so it's 15 meters per second, right? So between 10 and 20 seconds, the speed or velocity here is 15. So we're going to use 15, and remember our mass. I'm going to show you our mass again. Our mass here is 100 kilograms, okay? So we're going to say 100 multiplied by 15. All right, and we already know what exactly that will be. So it will be 100 multiplied by 15, which equals to 1,500, right? 1,500, and the unit for momentum will be, so you need to remember units as well, kilogram meters per second, okay? All right, so next part of this question now, we said if the object hits another object and immediately comes to rest, what happens to the momentum of both objects? So if this hit another object and it comes to rest, then what will happen is that the momentum will be transferred to the other object. All right, and so it itself stops, the momentum is conserved. So momentum is conserved. Remember that the law states that the momentum before collision is equal to momentum after collision. So therefore, that momentum is conserved, or it is transferred to the other object. All right, so the object at rest will transfer its momentum to the other object. Just to mention that, because this is not the two objects coming to rest. Only one object comes to rest. All right, so let's put that it is conserved. All right, so it is conserved. All right, it is conserved. That's what happened to the momentum. Or what you can say, it is transferred from the object at rest to the other object. All right, so the momentum is transferred to the other object. All right, let's say, or it is transferred to the other object. All right. All right, so that's what happened to the momentum. So it's a gaining momentum for the object that this object collides in. But last part of this question is using the graph above, calculate the total distance traveled by the object. So in order to go back and forth, I put the graph here. So we're gonna use this now to work through real quick. But what you need to do to find the distance, the area below the graph. So what I'm gonna do is to kind of break the graph up into different parts, and so that kind of help us to calculate the total distance. So I want to just go a little bit. All right, I don't like that line at all. All right, so let's take that line back out. All right, take that line. So I want this to be as straight as possible. All right, my hand is not usually straight, but let's just try. So here, this is one shape here. All right, good. And this is another shape here. All right, so that's another shape there. All right, coming down here now, this is not a perfect shape. So what I'm going to do is just split this part here into two different things. So like that. All right, so that will be all our shapes below the graph. All right, so next thing we want to do is to calculate now the area below these shapes. And so this will be half base times height. So just remember that this is a triangle, so it's going to be half the base times the height. All right, here is going to be base times height, because it's just, this is a rectangle here. Again, here's a rectangle. It's going to be base times height. And then here, the small piece is going to be half the base times the height as well. And another triangle here is half base times height. All right, so what we're going to do now, all right, to make life easier, let me just kind of work them out. This is base times height here, half base times height. So just kind of work them out here and make it easier for us. And then we just put the total as our answer. All right, so this will go faster. So the first one is half base times here is going to be 5. So the base here is 10, so it's going to be 5. And with 5 times 15, because the height here is 15. So this piece here is going to be 5 multiplied by 15. Okay. All right, so we're going to 5 multiplied by 15. And then this part here, base times height, and the base here is from 10 to 20, so that's going to be 10 and the height is 15, so there's going to be 10 times 15. All right, just to make it quicker, 10 times 15. All right, and so here now base times height. Again, the base here is from 10 to 30. So 10 to 30 is 10. And so the height again is 15. So it's going to be another 10 times 15. So 10 multiplied by 15. All right. And the small triangle on top of this rectangle here is going to be half the base. And the base is 10. So that would be 5. And the height is from 15 to 25. So the height there is the height here is 10. Okay, yeah, because it's 15 to 25, the height is 10. So we're going to say here going to be 5, half the base, which is 10. So going to be 5 multiplied by 10. Okay, so the height of this triangle there is only 10, moving from 15 to 25, right? So 15 up to 25, height is 10. This triangle right here, the base is 10, 20. So this is, if the base is 20, then going to be half of that base, which is 10. And the height of this triangle here is all the way up to 25. So it's going to be 10 multiplied by 25, right? All right, so once you do all of this and multiply all of them, you will get your answer. So I'm just going to put the result values here. So let me just write them out real quick. All right, so one value, which is the first one, 5 times 15 going to be 75. So we're going to have 75 plus, so 5 times 15 is 75. And then we're going to have a 10 times 15. And so 10 times 15 will be 150. So it's going to be 150. And there's another 10 times 15, which I'm sure, yep. So here again, another 10 times 15 here. So let's put that in. And let's go back again. So that is another 10 times 15, which is also 150. So let's say plus. All right, let me go back into this. So better here, yeah. So here going to be plus 150. And then you're going to be plus here, which is 5 times 10. And 5 times 10 will be 50. So let's put that in as well. All right, so 5 times 10 is 50. And then we have another one here, which is 10 times 20, 10 times 25. All right, so 10 times 25 is 250. All right, so plus 250. All right, so plus 250. All right, so we have 75, 150, another 150, 50, 25. All right, do we miss anything? Let's see, let me make sure, check. So I have 5 there. Let's check, I think is just to make sure. All right, I think we miss 1. All right, I think, no, that's all. Yeah, 1, 2, 3, 4, 5. Okay, good. All right, so if you add up all of these now, what you'll get here, all of this will give us 675, right? Add up all of this together, get 675 meters. All right, so that will be your answer in terms of the distance. All right? All right, so let's now jump into the next question, because this is the end of this question here. The next question reads that this question is about magnetism. All right, and this question 4. So we in the halfway question now. It says, in the space below, draw a bar magnet and label each pole, one being north facing and the other being south facing. I said draw lines to represent the area of the magnetic field. So all you need to draw is a bar magnet, and on the bar magnet you label north and south, and then you draw the magnetic field. So let me just quickly do that. So if this is my bar magnet here, I'm going to draw my north and south. It doesn't matter which way I draw it, the north or the south, but the ends must be north and south. Now, what's going to happen here, what you must do is to draw the magnetic field. So let's draw the lines first. All right, so you're going to have some lines running from one end to the other end. So you can draw any amount of line. Those really matter. But lines will come from one end to the other end. I'm also going to draw only one, just to kind of show the concept. Now, what is going to happen here, what you must have is that the lines must come out of north, running toward the south pole. Okay, so moving from north into south, north to south. All right, so what is going in is to the south. What is coming out is from the north. And of course, you could put more lines if you wish. Let me just put one more line just to kind of show you the concept here. You can put another line right there. All right, north to south. Another line right here, north to south. All right. So that's a magnetic field around a single bar magnet with north end and the south end. All right, so what do the the arrows, sorry, on the lines represent? So the arrows on the lines, what they represent is the direction of the magnetic force or the direction of the magnetic field. So there's two ways you could actually express this. I'm gonna put both of them. So this represents the direction. That is the direction of the magnetic force or the the magnetic field. Okay, so whichever one. So the direction of magnetic force or the magnetic field. All right. All right. All right. Good. So it's either or. All right. So the force is actually good. So I mean, if I said the magnetic field is also fine. So why is the field lines closer together near the poles of the magnets? If you notice the magnet, you notice the lines are actually closer to the ends, really. All right, and they're further apart out the sides of the magnet. So let's talk about why the lines are closer at the poles of the magnet. And this is here, the reason is, let's say, because the magnetic, field is stronger at the poles. Okay, so the magnetic field is stronger at the poles of a magnet, right? So that's why they're concentrated more at the end. All right, so definitely. All right, for part D, it's a list two ways in which a piece of steel bar can be magnetized. So how can you magnetize a steel bar? Two different ways, and one was a classic way is by stroking. So you can say by stroking. And stroking is actually called a rubbing method as well. So stroking or rubbing, but stroking is a word that they use to describe that method. You hold the magnet, the steel, and you stroke it with a permanent magnet, and it will become magnetized. The other possible way you could do this is by electrically, which is also called electromagnet. So this is electrically. All right, so electrically. All right, so electrically. And let's say electrically by placing it into a solenoid, just to make a note of that. Electrically by placing it, just to make it be specific, by placing it into a solenoid. All right. So it's really to create an electromagnet, right? So if you put the piece of steel in a solenoid, which is a coil of wire, all right, wrap around it tightly, and you put a current at the ends, then the steel will become magnetized temporarily, or they call electromagnets. All right, so next part question here is a piece of copper wire is moved vertically in a magnetic field between north and south. And between north and south pole. It's draw a diagram, a diagram to represent this and explain what happens in the wire. All right, so let's kind of draw it and explain. This is how many marks? This is a 3 marks. So I guess the diagram may be 1 mark and then 2 marks to kind of explain it, or 2 and 1, depending on what they're looking for in the mark scheme. So, but we're going to kind of just draw the magnets here. So we are going to have 2 magnets here, north and south. So we're going to have the 2 poles. Let's call it this side south. Let's call this side north. And remember, once you join the magnetic field, since it's like this, the lines will go straight across like that. All right. And just to make a mark in here, that the arrows must go this way. You also need to draw a direction. I guess they're going to look out for that as well, the direction of the magnetic field. And then what they're going to draw now is the wire. So this will be the wire going through the field. Okay, that's the copper wire right there. All right, so that will be a diagram. So that's a copper wire. You can, a matter of fact, please label them. So north and south, you can say north pole, south pole, just to make a note, is the poles of the magnet. And then this, you make sure you label as your copper wire. All right, so please label your diagrams as well. That's very important. When a good habit, whenever you draw diagrams, label to indicate what is what. All right, so let's explain now what actually happened in the copper wire. And so here is simple as this, that a current is induced. You can say a current is induced. All right, so that's exactly what is happening here. And so just to make a note right here, some extra notes just to make you understand right here. So if you move the wire faster, right, then what you're going to have is that you have a greater current, okay? So just to make a note, all right, just so you may need it somehow or sometime. So moving the wire faster will result in an increase in the current. All right, so just to make a note, the current. Just to make a note right there. So you may need that for some of the question in some of the exam. All right, or even the exam coming up, I don't know. All right, and so let's go to the next question. Question number 5. So this question is about electromagnetic radiation. So we're looking at now our EM waves, electromagnetic waves. And here it said, explain how X-ray can be used to obtain an image of a broken bone. So you get a broken bone, you go to the doctor, and the doctor take an X-ray and tell you exactly which part of the bone is broken or if you have a broken bone. And so let's talk about how now this is able to work. So the first thing is that the X-ray itself, right? So X-rays are blocked by bones. That's the first thing I wanted to note. X-rays are blocked by bones. They can't pass through the bones, right? The X-rays are blocked by bones. That's the first thing I want you to know. They're not able to pass through or penetrate the bone, all right? And of course, we will know why, because again, the short wavelength, right? A very short wavelength. All right, so here now is that, but what I want to make a note, so when it's blocked by bones, so at the bones, all right, it will generate what they call a white image. So at the bones, it will generate a white image. As a matter of fact, X-rays are black and white, if you notice that, right? So it generates a white image. That's the next thing I want to note. We're looking for 3 marks. The X-rays are blocked by bones. So at the bones, it will generate a white image. However, let's say at the crack, let me say however, at the crack, at the crack, let's use crack, or the broken area. So at the crack or broken area, let's put broken area in the bracket. All right, so at the crack or broken area, the X-ray, all right, passes through and generate a dark image. Okay, so it passes through and generate a dark image. All right, so the bones appear white, but the crack will appear black. All right, because as X-ray pass through it, all right, it appear to be dark. All right, so that will answer your question right there. So that's why you can notice, you can see the crack in the bone. Once you see in the dark area, know that this is a crack. However, the doctor will know differently if it's just a joint, because a joint, it will have small spaces. So you know, okay, yeah, that's a joint, and they know exactly the area. But the crack itself and a continuous bone, they will actually pick that up. All right, so for part B now, it said the wavelength range for visible light is approximately 400 nanometer to 700 nanometer. Calculate the frequency range for visible light, given that the speed of light is 3 times 10 to the 8 meters per second. So the first thing we want to do right here now is to convert these values from nanometers into meters, right? Because it's very important, because if we work with meters in the speed, we need to work with meters as well in the wavelength, right? So we need to keep our units the same. So a nanometer is 10 to the minus 9, just to mention that, right? So a nanometer is 10 to the minus 9. So if you have 400 nanometer, it is the same as 4 times 10 to the minus 7, right? So there's going to be 4. So 2 zeros actually taken off if you think about it. All right, so before times 10 to the minus 7. So just to make a note of that right there. So that's our value for our 400 nanometer. And the values for our 700 nanometer here will be it'll be 7, taking off 2 zeros as again. So times 10 to the minus 7. All right, because nanometer is to the minus 9. All right, so once you have that now, we have those conversions. So what you need to do now is calculate the frequency at each point. And remember what frequency is equal to. The frequency is equal to speed over wavelength, right? So frequency is equal to the speed over the wavelength, because wavelength is equal to frequency times wavelength, right? So that will be your formula to find our frequency, all right? So that's the lambda for wavelength. All right, so what we can actually do is to find the frequency here, and then we find the frequency here, and that will be our range, right? So the frequency at this point will be our 3.0 times 10 to the 8. Let me say 3 times 10 to the 8. So that is our speed. So 3 times 10 to the 8. All right, times 10 to the 8 divided by the wavelength here. All right, and the wavelength is 4 times 10 to the minus 7. All right, so we're going to divide that 10 to the minus 7. Same thing on this side here. You're going to say, okay, 3 times 10 to the 8. All right, let me. I think I need to go up. All right, right there, right. So 3 times 10 to the 8. All right, divided by, that's not 180. Let me just take that out. I really don't like how that look. All right, so let's put to the 8. All right, just to make our thing look better. All right, so I don't want no confusion here. All right, so times 10 to the 8. So times 10 to the 8. All right, and then that's going to divide now by this wavelength here. We're going to be 7 times 10 to the minus 7. All right, and so if you work these out, and remember on the calculator, you need to press the exponential sign, so be careful when you're pressing your calculator. So this is going to be 7.5. This is 7.5. All right, times 10 to the 14. All right, so times 10 to the 14 hertz, and this is going to be in hertz. 10 times 10 to the 7.5 times 10 to the 14 hertz. That's hertz is as in the frequency. Now, in the divide this, what you should get here is going to be 4.29. So 4.29 times 10 to the 14. Okay, times 10 to the 14 hertz. Okay, let's say this is the 0. Let's say 0 times 10 to the 14. Let's 14 hertz. All right, so that will be a range of your frequencies. So you can just say, okay, you put the smaller one first, which is 4.29 to 7.5 hertz. So that will be the frequency range from this to that. All right, so you can just make a note right there. All right, so that will be answer. So you work with the frequencies and just put the smaller one first. It ranges from 4.29 10 times 10 to the 14 hertz to 7.5 times 10 to the 14 hertz. All right, let's go to the next part of the question now, part C. It said X-rays are ionizing radiation, right? So X-ray are ionizing radiation. Identify one other kind of ionizing radiation found in the electromagnetic spectrum. And so the other one here going to be our gamma ray. And an easy way to know this, there's something I probably need to show you. But do you remember what I've used in the previous review? Is that let me just write this down first, and then I will explain to you again. All right, remember the order of the electromagnetic wave spectrum in terms of how they arrange, and also some properties you need to know again. The first thing we're gonna have is R. So we're gonna say radio. Remember, I said radio, my information verbally, right? Unless X news is gibberish. Remember that? So we're again to remember how they appear is that radio, my information verbally, unless X news is gibberish. All right, so that will give you the order of your electromagnetic waves. And just to point out right here is that the ionizing ones will start at the X-rays. So just to make a note here, only X-rays and gamma rays, these are ionizing. And then going this way, they are non-ionizing. So let's put I for ionizing. So these are the ionizing ones. And they could only ask for one because after the X-ray is only gamma. All right. And then the non-ionizing, let's put Ni. They are non-ionizing. All right. Just to make a note. So you need to know that as well. Easy way to remember it. Read my information verbally unless X news is gibberish. All right. I also need to know again the relationship here is that going from radio waves all the way down, we have an increase in frequency. So frequency here will increase, just to make a note right there. You have an increase in frequency. And going from radio all the way down as well, what we have is a decrease in wavelength. So wavelength decreases. All right. So R is for radio. All right. M is for microwaves. All right. Infrared. All right. Then we have visible light. Then we have ultraviolet. Then we have X-ray and we have gamma ray. All right. So again, radio my information verbally unless X news is gibberish. All right. So it said, what type of electromagnetic radiation is used to rapidly heat food? And everybody should know that. So that's like a mark they give us, and we use microwaves. So the machine that you use is actually called a microwave machine, right? But we just call it a microwave. All right. So it produces microwaves. All right. So microwave is the electromagnetic radiation that we actually use. It's a name two characteristic that all electromagnetic waves have in common. So one is that they're all transverse. Like that's the first one I'm gonna put. They're all transverse waves. They are transverse, and we know what transverse means, right? So once they are transverse waves, they are transverse waves, and which mean the wave particles are perpendicular to the direction, right? So, you can always do that one. So the wave particles, they are perpendicular, which means at right angle to the direction of a wave. All right, just quickly run through the others. And next one you could put is that they travel in a vacuum. All right, so can travel in a vacuum. All right. Also, again, another one you can also put is that they have, let's say, I'm writing gibberish now. They have the same speed as light. They have the same speed of light. They have, or move, let's say they move. All right, they move at the speed of light. In a vacuum. Okay? Yeah? So in a vacuum, they will travel at the speed of light. All right, so good. So those are the three major properties that all electromagnetic waves do have in common. All right, let's jump to the next question. Question number 6. And question number 6, it said this question is about energy and work. And so here's a figure 6.1 shows a simplified diagram of a 65 kilogram diver on a diving board. The height gained by the diver at the peak of his dive is 10 meters. All right, and gravity is taken as 10 Newton per kilogram. All right, so let's go down and see exactly what they're asking us to do here. It's a calculate the gravitational potential energy gained by the diver, all right, at the peak of his dive. And so the gravitational potential energy, given a potential energy, is simply the mass times gravity times height. All right, so it's mgh. So let's go for m, and let's go. We know our gravity is 10. So it's 10 here. The mass is 65, and our height is 10. So it's going to be 65 times 10 times 10. Okay. So 65 times 10 times 10. 65 is our mass. So 65 times 10, which is our height. All right. Let's say gravity because mg. So that's our gravity times 10, which is our height. And so what we end up with here is 6,500. And that's going to be joules. Okay. Energy is measured in joules. All right. At this point now, part 2 is to calculate the speed of the diver as he enters the water. All right, so what you need to know is that at the maximum height, he has potential energy. But coming down, the potential energy will convert to kinetic energy. At touching the water is a total loss in potential energy and a gain in kinetic energy. Because once potential energy is lost, you gain in kinetic energy. So what you need to know, what happened at the bottom, so at the bottom of the dive or the bottom of the ramp or whatever it is, or from the top to the bottom of the or to the top of the water. All right, so at bottom, let's just say at bottom right here. I want to show you what I mean by at bottom because I really wanted to understand this. So what I'm talking about is here. Coming from here, so this is the height I'm talking about. So from here, where diver is as his maximum, let's call it right here, to right here. So at the first point, I'm putting this stick right now. That's total potential energy. There's no kinetic energy there. Coming down, it is a convert from potential to kinetic energy. Here is only kinetic energy, no potential energy right here. So the total potential is converted to kinetic energy at the bottom right here. All right, just on hitting the water. All right, so let's go to look at the relationship I'm talking about. So at the bottom, there's a relationship that we must know. We must know this is that at the bottom we have potential energy, which is mgh, which you just calculate that on top there. So mgh is converted to kinetic energy, and kinetic energy is half mv squared. So it's going to be half mv squared. All right, so this is a squared, not a 2, right? So it's half mv squared. So it's converted totally to that. And so what we can do as a relationship here now is that we can say, okay, our mgh, let's just show you what our mgh was in the previous question. Our mgh is 6,500. So what we know that is our 6,500 is totally equals to half of mass, which is half m. Okay, so it's half mass times velocity squared. So what we need to do now, let me just do the rest with the pencil. So what you need to know now is that V, to find V, it will equal to, I'm just going to skip some steps so you can know exactly. You can just make V be the subject of a formula. You're going to go through a number of different steps to actually reach there. But some of you just look at this and know exactly. So to find V, it's equal to 6,500. So it's going to be 6,500 divided by half of mass, all right? Divided by half m, all right, over half of the mass. All right, so that would be V as the subject of the formula, the square root of 6,500 over half mass. And so therefore what we can have here is the square root of 6,500. Okay, so 6,500 divided by half the mass. And the mass of the diver was 65. So half of 65 is going to be 32.5. Okay, so it's going to be 32.5. All right, and so what we're going to have here now is the square root of 200. So V is equal to the square root of 200. All right, the square root of 200. And the square root of 200 is equal to 14.14 meters per second. So 14.14 meters per second. All right, so that is the velocity on hitting the water. All right. Next part of the question is a give the energy transformation that occurs as the diver descends into the water. So on top, remember he has potential energy, right? So what's going to happen here, coming from top, is that this potential energy will convert to, so let's say potential energy. So coming from top is potential energy. Potential energy. I can put an arrow right here. Let's put an arrow. Converted to kinetic energy, kinetic, and just on it in the water, and also sound, because some sound would given off by the splashing of the water, right? So there are two types of energy that is experienced at when a diver starts to descend into the water. So potential energy converted to kinetic energy, and also to sound and hitting that water. All right, so part C said the vertical height of the stairs is 7 meters. It takes 15 seconds to walk up the stairs. Calculate the work done in raising his body mass as he climbs the stairs. So if the height of the stairs is 7, and it takes 15 seconds to go all the way up to the top, then what is um, work done? So to find work, the first thing to remember about work is equal to force times distance. Let's put that right here, right? So work is equal to force times distance. But in this case, force would be is weight. So what I need to find is weight. Let's find force first. Okay, so force, which is weight. I could just put W there, but I don't want to mix up weight and work. So let's just say force. So his force, which is his weight, is equal to mass times gravity. His mass was 65, so going to be 65 times 10 equals to 650. So 650 is the force. So based on this now, we already know the distance, which is 7 meters. And so we're going to say, okay, work now is equal to 7 meters. Well, let's say 650 first as the force, multiplied by 7 meters, which is the entire height. And so therefore, this is equal to 4,550, yeah, 4,550 joules. I can say Newton meter as well. All right, so that's the work done right there. All right, now for part 2 of this question is to calculate the output power he develops when raising his body. So what you need to know is that power is equal to work over time, right? So power is equal to work over time or energy over time. So it's going to be work over time. That's what the power is equal to. So we already know what the work is, and the work is 4,550 joules, and the time that it takes, well, the time it took to go up the thing was 15 seconds. So yeah, that's 15 seconds. All right, so it took 15 seconds to go up the entire thing. So going to be divided by 15. And so what you get here will be 303.33 watt. All right, again, you can also put this as joules per second. Let us say, or joules per second. Whichever unit you want to use, that's also fine. So 1 watt is equal to 1 joule per second. All right, let's go to the next part of the question. Okay, that question actually finished. All right, question number 7 now, and we're almost there. It said the question is about light waves, right? It said at an annual eye examination, a student was required to sit 2.5 meters in front of a plane mirror and read off the letters on the eye chart, which is 3.5 meters from the mirror, as shown in figure 7.1. So the plane mirror is here. The eye chart is 3.5 meters away, and the person sitting 2.5 meters in front of the mirror. So those are very important bits of information there. And here now it said that for part A, it said, how far is a student from her image in front of the mirror? So how far is she sitting from her image in front of the mirror? So let's want to point out something quickly. Is that the image in front of the mirror for a plane mirror is the same as the distance behind the thing. So let's just put this right here and just make a note that the image will be here. So let's say image will be here. All right, and the image again will be 2.5 away. The image of the girl will be 2.5 behind the mirror as well as in front of the mirror, right? I mean, this is not drawn to scale. So how far is she sitting away from her image is actually 2.5 plus 2.5, right? And that is 5. So we're going to quickly let's work that out. So we're going to say 2.5 meters plus 2.5 meters, which is her distance in front of the mirror and the image behind the mirror. So that gives a total of 5 meters. So she's 5 meters away from her image. All right, so for part 2, is at what distance from the student's eye does the image of the letters being viewed appear? So what I want to note, what you wanted to note now, that the image of the letters will be 3.5 meters behind the mirror. So that's going to quickly put that. So the image here, all right, of the letters will be 3.5 meters behind the mirror. And so she now, from her eye, which is here, all right, and so it is 2.5 plus this 3.5. That's how far she's away from the image of the letter. All right, so let's quickly put that down now. All right, so she's going to be 2.5. The image is actually the 3.5, which is the image distance, the image distance of the letters, plus her distance, which is 2.5. All right, and so we have a total here of 6 meters. All right, they're going to be 6 meters. All right, let's go to the next question. It's a while. Okay, I've gone too far. All right, it's a right here now. It's a while looking into the mirror, how does the size of the examination room appears at this to the student in relation to the actual size? And for plane mirror, image and object are the same size, so this will be the same size. All right, nothing will change. All right, so in a plane mirror, everything looks the exact same size. All right. The only difference is that you have a lateral inversion taking place here. That's the only difference, but it will be the same size. Now for part B, it said upon returning home, let's go back a little bit. Yeah, upon returning home, the student wanted to investigate the properties of images in plane mirrors further. As a student cuts out letter O and place it in front of a plane mirror, as shown in figure 7.2. So O is the object as she cuts out, and then we have a plane mirror right here, and this is her eye. Let's see exactly what they asked us to do here. It said on figure 7.2, draw two rays. Now they asked us to draw two rays that reflect from O. So we need two rays coming from O onto the mirror, then onto the eye of the student. Onto the eye of the student that's shown. It's a complete ray diagram to show how the image of the letter O is formed in the plane mirror. So there's 3 things we need to do right here. All right, so let's just see if I could make mine straight as possible this time. So what's gonna happen here is you're gonna take a line come here, and you need 2 lines. So you're gonna do that. All right, so you're gonna do that. Let me take this off so you can see a little bit better as I go. All right, and then this line will come into the eye. Okay, so let's just come straight into the eye. You're gonna come into the eye like that. I'm trying to be as straight as possible. All right, it's not working out as I want it, but I just want to get the idea that this is going this way. All right, and so all right, I'll put this in shortly. The other lines. All right, so this line here now will come this way here. All right, and so when it comes there, it's gonna come into the eye right here. All right, so again, this is coming in. Okay, and this one is going like that. And so there's a little normal right here. You can just make a little normal. A normal should be there. A normal should be there. You can actually label them because each incident and reflected lines will have a normal. And so they ask us to continue now to show the object, the image will form behind the mirror. And so what you're going to have, I'm going to use broken lines. You're going to come up like that, come up like that, come up like that. And then this one going to come like this, like that, like that, like that. So the object will be, the image of the object will be here. So let's put O here and put I, which is the image. It's going to be right there. So when the person is looking into the mirror, her eyes will actually go into the image of the O, because going straight across, the O is facing the O, but when she's looking into the mirror, it's going to appear there. All right. So that's how it will actually look. All right. And so part 2 now is how differently will the image appear if the student placed the letter E of similar size, the same distance from the mirror as O. So now the person uses an E and not an O. So if you use an E, what's going to happen here now is that it will look inverted. So if you turn the letter as normal, it's going to be inverted. As a matter of fact, anything in a plane mirror is laterally inverted. So left becomes right and right becomes left. But with the O, since both sides are the same, you're not going to see the difference, right? So here it's going to appear as laterally inverted. So it's going to be laterally inverted. All right. Or you can make a note. Let's just put quote here, or sideways, right? So lateral inverted means sideways, right? Just to make a note right there. It actually look like that, sideways or laterally inverted. Here's a give the term used to describe a type of image formed in a plane mirror. And the image that formed in plane mirror, we actually call them virtual images. So it's virtual. The term that you use to describe image in a plane mirror is virtual. All right, so here now, so the student then places the O 6 centimeters in front of a concave mirror of focal length 4 centimeters. State two properties of the image formed. And the image formed, as we've been through this already, but I'm going to show you just for you to understand it. So if you do not know why, I will actually show you. So there are actually three properties here, but they're actually for two. And one of those properties is that the image will be real. And I'm going to tell you why. I'm going to show you actually why. Not even tell you, but show you. It is real, is also inverted, and it's also magnified. So any of these three that put will be correct. Now, how this actually work is this. I already draw on these, so you don't have to worry about the time I'm going to spend to draw it. I'm going to do it real quicker because I actually have it. So I already draw the mirror. I also draw my F, and I also draw my C. So F and C, remember that C is twice as F, right? It's 2F. C is same as 2F. All right, now mine is at drawn to scale. So let's do a rough thing. So actually the rough thing will kind of help us to do. So first line, whenever you're doing this, the first line again, remember I tell you, it must come from the top of the object and run parallel straight across onto the mirror. So it's parallel to the principal axis, right? Then what you're going to do is to take a line now and run through here, through F, to where the line from the object actually meets the mirror. You're going to have that line. The next thing you want to do now, after you have done that, you want to run the next line now from top of the object straight through C or 2F. I say run it straight through C or 2F, so it's going to be like that. I run straight across. I must make it. It don't. Well, motherfucker, if you go through the mirror is not a problem, but the fact that it must go through the top of the object and also through 2F. So you have the lines like that. Now, where the lines meet, now you're gonna draw your image. So your image will be here from this point all the way up. And notice if you look at it carefully, what you notice is that the object, the image, let's put I right here. This is the image here. The image is inverted, which means turns upside down compared to the object. So it's inverted. That we have inverted. It's larger. So notice obviously bigger than this. So it's larger. So it's magnified. And it is formed in front of the mirror, which means it's real. So it's a real image, magnified image, and also inverted. All right. So remember your three lines you need to draw your image from a concave mirror. All right. In some cases, based on where the object is, because the line must go through the closest point, whether through F or 2F. So sometimes two lines could go through F, which I showed that method on the previous paper. All right. So just remember how to practice to draw these things. All right. So question number 8 was a final question. All right. So this question is about electricity. Now, it's a student now set up a simple circuit to investigate the basic properties of series and parallel circuits using a 6-volt battery, a 3 ampere lamp, and a resistor of 4 ohms. So, sorry, this is a 3 ohms lamp. I said 3 amperes. A 3 ohms lamp and a 4 ohms lamp as well, as shown in figure 8.1 and 8.2. All right, so we have 3 ohms, 4 ohms, 3 ohms, 4 ohms are the same. Just one is in series, one is in parallel, and that's the only difference. So one is a series circuit, one's a parallel circuit. All right, so before I even jump on answering the question, I just want to kind of remind you about something quick, is that in a series circuit, the current is the same throughout the entire circuit. So current is the same. All right, I could put I because no I is current, right? All right, so I equal the same. All right, let's put current. Current is the same throughout the entire circuit. However, no voltage for this voltage or volts. So voltage is shared. So it is shared among the components based upon the resistance. All right. So based upon the resistance, the voltage is shared. Now, the opposing thing happening for parallel circuit is that the current is shared in this one. The current is shared among the component, and again, it's based up on the resistance. So current is shared. All right, current is shared. All right. And voltage, let's put voltage here. So voltage now, I think I missed something. Okay. All right. All right. So, right. I think I'm in a little bit difficulty. All right. So, okay, good. All right. What? This is, all right. No, I get it. Okay, good. Now I'm back on track. I think. Okay, yep. So if I go to draw, just type right here. Good. So now voltage now. I don't know why at the end this want to give some problems, right? The voltage is the same in a parallel circuit. All right, so using this circuit shown in figure 8.1, calculate the current flowing through the battery. So to get the current flowing through the battery in figure 8.1, which is the series circuit, what you need to learn first, or what I actually need to know, we need to find the total resistance, right? Because to find current, we're going to use from this formula, V is equal to I times R. So if V is equal to I times R, then I is equal to V over R, right? I is equal to V over R. So you need to know what R is, which is total resistance. And so the total resistance in this circuit, so let's just say R in this circuit is the total resistance is equal to R1 plus R2, okay? So you're going to equal to 3 plus 4, all right, which equals to 7 ohms. They're going to be equal to 7 ohms. And then now, so current now will equal to, as I'm saying, is based on the formula, current is equal to V over R. So let's put that down. Current I equals to V over R, all right, which equals to V, which is V over 6 volts. So 6 volts, if you look at the diagram, I have 6 volts. Let's look at the volts. So 6 divided by R, which is 7. And so what we have here, you're going to get 0.86 amperes, 0.86 amperes. All right, so that there is the current through the battery. All right, so let's go to the next question. So the current through the entire circuit is that, right? It's a voltage across the lamp. So we want to find the voltage across the lamp. We know our current. Remember, the current is the exact same thing, so we already know our current. But the voltage across the lamp, let's see which one is the lamp. The lamp is the 3 ohms, right? The lamp is a 3 ohm. All right, so since we have our resistance, 3 ohms, and we have our current, again, from the formula, V is equal to I times, so V is equal to IR. So let's make sure V equal to I times R. And so I, we already know our I, which is our 0.86, is going to be equal to 0.86 multiplied by resistance. And the resistance of the lamp is 3. So it's 3 ohms. So therefore, what we get here is 2.58 volts. All right, so that's the voltage across the lamp itself. All right, let's go to the next part of the question here. It's using the circuit shown in figure 8.2, calculate the total resistance. And so the total resistance can be calculated in 2 different ways. All right, so I'm going to show you. And this is only for 2 resistors. If you have 2 resistors, then you can use a short formula. So here now, the 2 resistors is 4 and 3. So let's calculate the total resistance as they asked us to do here. So we're going to find the total resistance in the parallel circuit, and that is 2 lamps. So again, there are 2 different ways you could do this. You can actually use the formula that 1 over, which is the total, let's say 1 over the total. So 1 over the total, 1 divided by the total resistance, equal to 1 over R1 plus 1 over R2 plus 1 over R3, right? So 1 over R1, I'm going to say, let's call it R1, plus 1 over R2 plus 1 over R2. All right. And if you have more, you could just keep on doing like that. But since we only have 2 resistance, or there's a next formula you could use here. So next formula, and this only work when you have 2 resistors in parallel. If you have more than 2 resistors, you can't use this formula, right? So the next formula is actually the product over sum. So this is going to be R1, which is the product, R1 multiply by R2, right? All divided by R1 plus R2. Okay, so just put all of this in bracket. All right, and the R1 and R2 will be subscript just to make sure a note of that. So what we're saying is that another formula is the product over the sum. The product over sum is a short formula to use to find out the total resistance in a parallel circuit only if you have two resistors. All right, and you can do both methods and see if you're actually correct. All right, so let's just quickly see if we can just do that real fast. All right, just to kind of show exactly how this actually work out. Real quick. All right, so here now as this one, let's work this out on this side real fast. So here now 1 over RT, right? So let's say 1 over RT, which is the total resistance. 1 over RT is equal to 1 over R1, and 1 over R1 is 1 over 3. One of them is 3, plus 1 over 4, okay? Plus 1 over 4. All right, and so what we get here, you can just do it like this. Just okay, let's use 12 as our common multiple right here. And so this into 12 goes 3 times, 412 goes 3 times, so 3 times 1 is 3, so let's put 3 right here. All right, and then 3 into that goes 4 times, so it's going to be 4. So here now we have 7 over 12, so 1 over R, let's put this as a thing right here. So 1 over R, which is the total resistance, is equal to 7 over 12. All right, so 7 over 12. Or we can simply say that R is equal to 12 over 7, okay? So 12 over 7, so it's going to be 12 over 7. And 12 over 7 is equal to 1.2, 1.21. So the answer here, so R is equal to 1.71, 1.71 ohms, right? Now on this side, we say product over sum, right? So the product, again, it is one is a 3, one is a 3 ohm. All right, so one is a 3 ohm, one is a 4 ohm. So we're gonna say 3 times 4, right? 3 times 4 divided by the product, which is 3 plus 4. All right, and so 3 times 4 is 12. All right, just ignore this foolishness. All right, let me just erase it. All right, so again, 3 times 4 is 12. All right, so we're going to get our same answer, 12. And 3 plus 4 is 7. So it's going to be 12 divided by 7. And so what we get here is I missed my point. So this is 1.71. So here you're going to get the same thing here as well, 1.71. So get 1.71 ohms. All right, so whichever method you use, you get the same thing. So if you have two resistors in parallel, it is the product of the resistors over the sum of the resistors. Or I can just say 1 over R, which is the total. So 1 over RT plus 1 over R1 plus 1 over R2. And if you have more, then you can keep on doing like that. All right, so for part 2 now is to calculate now the current flowing through the lamp. So we already know our total resistance, right? And so let me just quickly show you our total resistance here. Let me just go back. I want to find the current in the lamp. Let me just go back to the diagram because we need something very important here. Let's give you the formula before I have to jump to that. So the current again is equal to V over R. So current equal to V over R. So the first thing, V divided by R. The first thing we need to know is our voltage, and let's go back to resistance up here. So let's go quickly. All right, so the total resistance is that. So in this one, the lamp here is actually 3. All right, and the voltage here is 6. So the voltage across both of them will be the same. Remember that the voltage is the same. So voltage across the 3 ohm is the same. Voltage across the 4 ohm is also the same. So the current at the 3 ohm, we're going to use our 3 ohms, which is our lamp. So let's go down and calculate that. So our voltage is 6, and our resistance of the lamp is 3. So therefore, the current going through that is going to be 2 amperes, okay? The current is 2 amperes. All right, the total current now, if you want to find the total current now, is a different story. Actually, multiply the 1.7 times the 6, right? Which will give you the total current. All right? All right, so let's go to the next part of the question here now, which is the last part. It's to explain why a metal wire is an electrical conductor, but a plastic is used as an electrical insulator. And very, very simple here is that metals, and this go for all metals. So metals have free electrons, all right, free electrons, all right, so free electrons, all right, free electrons that allow current, all right, that allow current, to flow through them, right, to flow through them. All right, so that's the first thing. So metals have free electrons that allow current to flow through them. However, no, um, however, plastic, however, plastic, do not have free electrons. As a plastic do not have free electrons, do not have free electrons. All right, do not have free electrons. Hence, prevent the flow of electrons, the flow of current. Hence, prevents the flow of current. Or I can say oppose the flow of current, right? So do not allow current to flow through because current is a flow of electrons, right? All right, and so then therefore, if current can flow through plastic, it is an insulator, and of course, metals are free electrons, so they will allow current to flow through them. All right, so that is the end of this review here. All right, thank you for being here, and again, I'll catch up with you soon. So be safe. Good luck on the examination.